manometers. These are devices to measure pressure, basically. And the whole thing works on the idea that at a horizontal line, the pressures are equal. So there's an example I've got on the screen there, which looks like a tube across the top with 3 columns. There's another dead here. Right, so, and what we're looking at here is a fluid in the bottom, which is at different heights. Yep. Okay. And you'll notice if you look closely that at the top, the tube across the top's got a constriction in it. What's going on here is that there's air probably flowing through here, and when it flows faster, there's less pressure. So the pressure in this piece is less than the pressure is in these pieces, the pressure due to the air. So what the way a manometer works is if you think about a line, so if we draw a line across here, for example, any horizontal line, then the pressure, total pressure down on that line is the same at all points. So at this point, you've got that head of whatever the gas is, plus that head of the blue stuff. At this point, you've got that head of the gas, plus that head of the blue fluid, whatever it is, water, what looks like blue dyed water to me. Okay, so the fact you've got more water here means that the air pressure here must be less. It sort of effectively sucked up the water at that point. Okay. So key thing with a manometer is draw a horizontal line and recognize that at all points above that line, the pressure is the same. And that gives you enough information to work out what's going on. Okay. That's the big picture. So you use a bit of number crunching, a bit of algebra to work out what's going on. Okay, so draw a horizontal line, and there's usually a smart place to draw it. So the smart place to draw it in this case would actually have been through there. Those two are at the same height in this case, I think. Are they? Yeah, maybe not. If you draw it across there, then you don't have to worry about adding these little heads of pressure. So we'll show you what I mean by that. Okay, so that's a, yep, so that's just the PowerPoint showing you exactly that the horizontal line in the shared well, the pressure's the same at all the points, so those 3 pressures, total pressures, are the same. Okay, there's 2 basic types of manometers. There's what's called open-ended and, surprisingly, closed-ended. So an open-ended manometer would be something like, we've got a bulb full of gas, and we're trying to work out what the pressure of the gas is, and you've got a tube with some stuff in it, and it's open to the atmosphere. So copying the thing, there's a picture of what it looks like. So you've got your fluid in the tube, and we're trying to work out what the pressure of this gas is what this will let you do. So effectively what's happening is you've got atmospheric pressure down there. Let's pretend that this is mercury in the tube. So this is mercury, and as Liam's already told us, the relative density of mercury is 13.6. Okay. So if that's the relative density, the absolute density, the actual density, will be 13.6 kilograms per square meter, cubic meter. Cubic meter, it's a volume, cubic meter is right. 13.6 kilograms per cubic meter. Wrote it right, said it wrong, autocorrect. Phew, got it. Okay, so we've got that situation, and we need to know what the height differences are. So my horizontal line I'm going to put here, and let's say that this is 25 millimeters. Yeah? And the question is, what's the pressure of the gas? And all you need to do is, you just need to do that acknowledgement that at any point above that red line, the pressure is the same. So whatever pressure is being exerted by the gas has got to be equal to the total pressure at that point. And because it's open at one end and closed at the other end, we do need to worry about atmosphere, because there's no atmosphere counterbalancing at this end. So the gas here is counterbalancing both the atmosphere and the mercury. Yep. So P1 is equal to P2, which in this case is the density of the mercury plus the density, not the density, good grief, pressure of the mercury plus the pressure of the atmosphere. Atmospheric density, I'm going crazy. Okay, and the pressure of the mercury, we can calculate rho GH plus atmospheric pressure, we've got a number for. And then we just plug some numbers in. So mercury is 13600 times G times that height. Put it into meters, plus atmospheric, which I'll put in pascals rather than kilopascals, because I've got this lot in kilograms per cubic meter, meters per second squared, and meters. So this is all in base SI units. So let's put this one just in pascals rather than kilopascals. So the whole answer should come out in pascals. And the answer, Levi, you got it there? Still working. See those fingers going? Yep, and then add on. Yep, that sounds right. What did you come up with, Levi? So you 46? 1046. Okay, and that's just in pascals. So what are we talking about here? We're talking about 104.6. I'm a little bit nervous here, Levi. I think the answer should be 104.7, we'll call it, kilopascals. But I'm a little bit nervous about what's going on here. Did you get this one? This is 101,300. I was a little bit nervous about the number of decimal places we got here somehow. So this is how we go here. Who else got a calculator? You got a calculator? What did you come up with? 104,635.4. That makes more sense. We had an extra 6. Okay, now we're cooking. So 104.6 kilopascals. Problem solving. So these for the heights? Yep. Okay, so the only top point you had is the top of the mercury, which is 25 millimeters. So it's got a 25 millimeter head of mercury. This thing here? No, because that's the gas pressure is going to be pushing. Technically, yes, there would be if it was a gas that had a really high density. There will be, whatever that height is of the gas will make a small difference. Yeah, so again, so this air in here, it doesn't matter how high that column of air is, as long as it's open, it's just going to be atmospheric pressure. So you're looking at what things there are above the line. So on this side, just the gas, with a head we'll ignore, and on this side, there's the mercury plus atmosphere. Yeah. And the reason I was really nervous about Levi's thing is that I know that 25 millimeters of mercury is less than 1 atmosphere, a lot less than 1 atmosphere. So it couldn't suddenly go up by 10 atmospheres. So I knew that the number had gone a bit wrong somewhere. It was only going to make this is small compared to atmospheric pressure. Yeah. So I knew it couldn't change it by that much. But you are right, Scott. There is technically a head of gas here I'm ignoring. So if this gas is it's less than 25 millimeters, so it might be 15 millimeters of oxygen or whatever the gas is, will not affect it at all. We'll do one when we do the double-ended one. We'll do one where you definitely have to take that into account.